Firstly, the question about this word interior angles. So the angles below, you can see, have got on them marked some of the interior angles. So I wonder if you could pause the video and have a think about what those interior angles might be. Here are three isosceles triangles, and these three isosceles triangles have been given different marks in them, and we have got, you can see there are some lines here on each of the triangles, and there's one line marked, and this indicates that these two sides of this triangle are equal in length. So you've got one here and here, so these two sides are equal in length, as are these two sides here. And that tells us that it's an isosceles triangle, because isosceles triangles have two sides which are equal in length. And also a property of an isosceles triangle is that they have two angles which are the same. So you can see that here we've got 48 and 48, and we've got our 30 and 30. Obviously, if all the angles were the same, all the sides are the same, we'd be looking at an equilateral triangle. But for this case, we've got only two sides are the same and two angles are the same. So we're talking about an isosceles triangle. We're not talking about a right angle triangle. There's no right angles in these triangles. And we're also not talking about a scalene triangle, which refers to the fact that there is no sides the same length or no angles which are the same. So hopefully with that little bit of information and extra knowledge, you have identified where the interior angles are within these three isosceles triangles. And these are these numbers here that indicates the degrees measurement of the angles, which are inside these closed shape, these closed polygons. So a polygon, the word poly is meaning many, so it's a many-sided shape, and these are straight sides. So when we're talking about polygons, we're talking about two-dimensional plane shapes that have straight sides. So you get examples of these: triangles, rectangles, pentagons. They can be regular or irregular. The important feature of polygons are that they have straight sides to them. So any shape that has a curved side is not a polygon, like a circle that we're quite familiar with, and some of these other maybe more unfamiliar shapes. If it's got a curved side to it, it is not a polygon. But if it's got a straight side, we are talking about polygons. And I'll try to keep using that language throughout the lesson. Prove to ourselves that actually we can use this help sheet that Mr. Gunn has provided for us, so that we can know that all the interior angles of these shapes do add up to that total within the middle. So we're going to check that he's been providing us with the correct information. So in order to do this, I'm going to ask you to see if you can get yourself a triangle. You will need to make sure your triangle has straight sides, so it's not got any curves to it, so it's a polygon. And we're going to watch a little video now so you can see what it should look like, and might want to follow along the steps as you do it. But what you're going to be doing once you've created your triangle is you're going to be cutting off the angles, cutting off the corners of your triangle, and then rearranging them and together along a line. Okay, so what you'll need to do is you'll need to label, as you can see, the various corners on your triangle and your angles, and then cut off, as we've just talked through, the different angles, the different corners of your shape. And then you need to rearrange them together along a straight line. Hopefully you'll see this able to work. Give you a chance to do that. And you will probably start to recognize and see that actually they do fit together along a straight line. You can almost provide yourself with an extra additional tool and put a ruler there so that you can check that you're along that straight line and it's really nice and straight. Okay, and just make those fit in exactly as you want them to. So hopefully by that short demonstration, you have been able to recognize that when you are thinking about putting your shapes along, your angles, along a straight line, you can use them to create this straight line and therefore see how much the total interior angles total up to. And we know something about angles along a straight line from our lessons on the beginning of this week. And we know that on a straight line, all the angles will add up to 180 degrees. So this is a way of proving that a triangle's interior angles also total up to 180 degrees as given on your help sheet, so we can know that the interior angles of a triangle are 180 degrees. And this works for any triangle, whether it be regular or irregular. And you've probably created your own irregular triangle, whether it be isosceles, even a scaling. You might have even been lucky to try and create yourself an equilateral triangle if you were being particularly accurate, or you might have had a right angle triangle. Whatever the case, as in the video, you can cut off those corners, cut off those angles and rearrange them to be able to make a straight line. So proving that within a triangle, within a three-sided polygon, the total number of the interior angles is 180 degrees. You can see on this demonstration that actually at either whatever corner I'm dragging, whatever vertices I'm touching upon and changing, the total of the interior angles is always going to be the same. It's always going to be 180 degrees, and that is always the case with any type of triangle. So it's whatever vertices I'm moving, vertex I'm moving, you can see that is still the case. Okay, so if we now go back and do the similar investigation, but this time we're going to be thinking a little bit about a quadrilateral. So what I'd like you to do with this quadrilateral, and you must make sure you've got straight sides to your quadrilateral, you're going to cut off the corners, the vertices, and the angles from your quadrilateral, and you're going to see what you can make using these angles. So I'll give you a bit of a tip in the triangle, but have a go with this quadrilateral. So make yourself a quadrilateral, any four-sided shape. Cut off the vertices, cut off the corners, cut off those angles and reconstruct them to see what you can make. See? So in this case, we haven't labeled it with the letters. We've just got numbers there for each of the vertices, for each of the angles that we're talking about. And you can see it being very slowly rearranged into, well, you might have had the same success, into a circle format there, circle shape. So all these angles are around a point, and so that should be starting to ring bells already, total up to 360. So that is a way of just proving to you that the interior angles of any quadrilateral are going to be adding up to the total 360. So it just proves the information that we've been given on our help sheet. So this is just the starting building block as a pictorial representation, if you like, of how we can know that there are 180 degrees in every triangle. Now we know that obviously when it's coming to equilateral triangles and regular shapes that the angles are the same, but we know that every shape, whether it's irregular or regular, the interior angles will still add up to the same as over here. So three-sided shapes, three-sided polygons will add up to the interior angles being 180, and four-sided, well, quadrilaterals, polygons will always have the total interior angles being 360, five-sided for 540, and six-sided 720, etc. and so on. One of the first activities you're going to be asked to do is look at the interior angles of regular shapes. And just to clarify and remind you that when we're talking about regular polygons, regular shapes, We are talking about shapes that have the same length sides and the same angle, all the angles are the same inside them. So on your help sheet today, which you have hopefully got with you, you have got some of this information given to you already. So you can be referring to that to help you solve these calculation problems. So you can see that in an equilateral triangle, all the interior angles total up to 180 degrees. And we're going to explore that a little bit further in a moment. And in a square, where all the sides are equal, obviously, all the angles total up to 360. As for a regular pentagon, 540, regular hexagon, 720, regular heptagon, 900, and a regular octagon, 1080. So that's the total of all of the interior angles added together. And if we're thinking about regular shapes, or we're trying to find out how many degrees in total the interior angles total up to, there is a formula that we can use. So this formula is on your help sheet, and it sort of has two stages to it. One that's useful for all polygons, whether they be regular or irregular, and the second part of the equation that you've been given will help you with this formula to find out the degrees that each of the angles are in regular shapes. So this is the formula. You don't necessarily need to worry about this today because you'll have your help sheet to refer to. But if you're in a position and don't have access to the help sheet and you wanted to calculate how many degrees in total the interior angles would calculate up to, then this is a way in which you can do it. So there's almost a step 1 and step 2 to this. So if we have a look at this equation, if we look at the top of it, this piece of information here will give us, for any shape, we can use this bit of the formula to work out what the total of the interior angles will be. So if I look back at our pentagon, we actually do know the answer to this, but we can sort of use that to work backwards if you like, so you can see how this formula can be used. So if we start with our 100, oh, let me change the colour so you can see quite clearly. So we've got our 180, and we're going to be timesing it by n take away 2. And you will have noticed on the formula, there's a little code here that says that n equals the number of sides that we are referring to. So in this case, we're referring to 5 sides because we're talking about a pentagon. So I'm going to put my 5 there. And when we're talking about how we calculate this, we are going to be thinking about the use of BODMAS. Now, if you remember from BODMAS, we're starting with our brackets first, and then we're going to be doing our multiplication afterwards. So we have got here, if we write this out, we've got 180, and we are going to be, we've already done this brackets, this calculation within the brackets. So 5 take away 2 is 3. And that will give us the number of degrees that are in the total of all the interior angles of a pentagon added up together. Okay, so we've already found for this shape. Now I can apply this to any shape, this formula. So if I was thinking about a 11-sided shape, I could use that to unpick how many degrees in total there would be of the interior angles of that shape. And then if we're thinking now the second stage of our working, and we're looking at wanting to, oops, let's get a different color, might help us. We're thinking about the second stage and we're wanting to look at a regular polygon of that shape. So this only applies to regular shapes. Then for the regular shapes, we can then use our total, and our total in this case being 540 degrees. And we are going to divide that 540 by the number of sides. And so in this case, we're talking about 5 in our pentagon. So that n represents the number of sides, 5. And then we can do our 540 divided by 5, and that will give us what one of the angles in this regular pentagon will be, one of the interior angles will measure. And obviously we can apply that because 180 would be the same on every angle within a regular pentagon. So this formula, part of the formula here, really refers to all the way we can find out the interior angles of all polygons. And this will help us find out one angle within a regular shape. So there's a difference between that. So a little bit like the angles along the straight line, angles around a point, we've been given some information, and actually we know some more information about interior angles as well that will help us approach this problem. So we know we're talking about the interior angles, we know we're talking about the angles inside this closed polygon. We are looking at what our missing angle is. We know something already about this shape because we know this is a triangle shape. And this triangle shape is, we know it's a triangle because it's got 3 sides. And we know something about all the angles, interior angles, what they total on a 3-sided shape. And as we've already explored, we know that the total interior angles on a triangle is 380 degrees. We also know that these are 2 angles already known to us. So we've got our 38-degree acute angle there. And we already have information about our obtuse angle, 123 degrees here. So we've already got lots of the information that we need. We are looking for this missing angle and working out what that could be using the information that we have been given. So, and the first thing that we need to do is find out what we know so far. So far, we know that with these 2 angles that are known to us, 123 plus 38, we have got 161 degrees of interior angles already known to us. So with that information, we can move straight on to working out what our missing angle is in a similar way to we've been thinking about angles along a straight line earlier on in the week. So if we now do 180 degrees and we're going to subtract what we already know is our 161 degrees, we will see what we are left with, our missing angle, which is actually in fact 19 degrees. So we can start filling that information into the diagram, into our bar model and into the diagram. And then we can check that we have indeed found the correct missing angle here, because if we were to add together our amounts, so we've got 123 here, plus our 38, plus our 19, which we've just uncovered. Sorry, my noise a bit funny there. This will get us back to our total of 180 degrees, which is the sum total of the interior angles of a triangle. Now we can use some further knowledge about our knowledge of quadrilaterals and also our knowledge of some of the missing angle work that we've done previously. So if we have a look here, you can see that we're dealing with a quadrilateral, we're dealing with interior angles, so the angles within this closed polygon. We know it's a polygon because it's got straight sides. So we already know that if it's a quadrilateral, the interior angles will total 360. So we can put that as our whole that we know, because the interior angles will in total up to 360 degrees. We know some information already about the angles within this shape. So we already know we've got 75 degrees, and we know, so that's our angle there. And we also know that we have got our 70-degree angle. we haven't got any number information here, but hopefully you will remember from our learning earlier on the week what this symbol tells us, and that says that we've got a right angle on this shape. So therefore this will be a 90-degree angle here, which we can add to our bar model of information. And obviously we are still trying to find out what our final missing angle is going to be. So we don't know that one yet. So similar to before, really, we're going to be finding out firstly what we know, and then find out what we are left with that will be our missing angle, because we already know this information that all the interior angles of a quadrilateral will always add up to 360, and we had a go at proving that a little bit earlier on. 235 degrees are known to us, and therefore we can then work out the missing angle. So if we do 360 and we subtract 235, we will arrive at our missing angle. Our missing angle in this case is 125 degrees. So we can put that missing angle back into our bar model. That will therefore give us a chance to check if we added all these parts, would it make our whole 360 degrees? And obviously add that back into our diagram, because we now know what that missing angle is, that X that was there. If we just look at this language of exterior angles, we're talking about angles which are outside our closed shape. So yesterday we were focusing on the interior angles. Today we're looking at the exterior angles. So it's just, you can see the difference between the two using these two diagrams, that we're going to be talking about exterior angles on shapes today. Complicated when we're asked to investigate the exterior angles of these shapes. So we're still looking for the exterior angles, and as you can see we've got one missing here. But before we even get to that point, we've got a first step to this problem to solve before we can get on, because we don't know our missing angle here. So we need to find that out in order to work out this missing angle. And in order to find our missing angle here, to start off with, so we could almost label this a different letter, I'll label that B if you like. We need to use our knowledge of the interior angles of a triangle. So we know from our previous knowledge that 180 degrees is the total number of interior angles on every type of three-sided polygon and every type of triangle. So we already now know some information, and we can work out that missing part that we need to be able to be successful at the second bit of our problem. So if we've got here, we've got our 70 degrees that we already know, and we've also know that there are 80 degrees known to us, and we are missing our information about this part, this angle here. So like we have done before, we will need to work that out. Firstly, we will need to work out if we have these two totals put together. So if we have our 70 plus our 80, we can then know how much we're going to be taking off our total to find out what is left. So if I just here, if I put here a bit of a brighter colour so you can see against the blue, if we're doing 70 plus 80, we should recognise that we are going to be at 150 degrees that we already know about. So we can almost put that information onto our bar model, that these two sections together will give us our 150 degrees. Just about fit that in there. And from that, we can also work out what B will be. So if we do 180 and we take away 180 degrees, sorry, we take away 150 degrees from that, should already be able to spot what that might be. So we're doing 180, take away 150, we get 30 degrees left over. So we're dealing with a little acute angle there, which is our B. So if I put that back in our equation, so we've got here is 30, and we can put that back in our diagram here, being 30. So now we have all the interior angles. We can always check that, because obviously we can put that back in the original adding. So we could do 70 plus 80 plus 30, and it gives us our total interior angles totaling up to 180 degrees. Then we're going to be using the same information to transfer onto a further bar model to explain what we're going to be doing. So we're now looking along another straight line here. Now, it doesn't matter that the paper's orientated slightly differently. As I've said quite a few times now, you can obviously turn your paper around. You can see that that is a straight line there, even though it looks a little bit different. So you've got your straight line, and we know that angles along the straight line equal 180. So we've got our total, and we know that's 180. We already know what B is because we've just calculated that in our first step of our problem, and that was 30 degrees. And our next job is to work out what is the missing information to find out the A, this angle here. So if we do 180 degrees and we subtract 30 degrees, you should already be thinking, oh, I know what that one's going to be. We have our 150 degrees. So we know that A on this diagram here is 150 degrees. So if I put in my measurement 150 degrees here, and I can always check this because I know that this obtuse angle and this acute angle together should give me my angles along a straight line, which is 180. So if I've got 150 and I add on 30, then I can find out that I have got back to 180. So I know that that angle, the missing angle here, is 150 degrees.